3-7, graphs of rational functions. Just going to apologize in advance for the lovely lounge singer voice here that I have going on. Lovely first cold of the season. All right, so graphs of rational functions. So what we're going to look at today are sort of some of the characteristics of the different graphs of things that are made up of a ratio. So rational comes from the word ratio, and it's a ratio of two polynomials. That's what a rational function is. So of two polynomial equations. So that could be anything f of x, g of x that have like degree 1, degree 2, degree 3. So that's all a rational function is. So like an f of x over a g of x. So it could be linear over quadratic, whatever. When you look at graphs like that, we have a lot of different things that happen, things like asymptotes and undefined places because it's a ratio. So the parent graph for all of these is the graph 1 over x, which I know you guys are familiar with, but I'm going to go ahead and make a sketch of that just so we can look at that. So the graph 1 over x has two different types of asymptotes on it already. First one comes from the denominator. X can't be equal to 0, so whatever makes that denominator 0, which would be 0 in this case, would be our vertical asymptote. It's not removable, like we talked about the difference between an infinite discontinuity and a point. You can't get rid of that x, you can't factor it out. We're stuck with x equals 0 as an infinite discontinuity. But the other kind of asymptote 1 over x has is horizontal. So let's talk about that. The horizontal asymptote is what the end behavior of the graph is. What is it approaching? When you look at the entire ratio 1 over x, as x gets bigger and bigger and bigger, the value of the fraction is going to get smaller and smaller and smaller. It's like 1 over 10, 1 over 100, 1 over a million, 1 over 10 million. It's going to get smaller and smaller, and it approaches, but doesn't equal, 0. So the horizontal asymptote would be y equals 0, the horizontal line. And then we have some other points on the graph. We know where those are. So 1, 1, -1, -1 has that origin symmetry. So this parent graph idea, if we know what happens to the parent graph, then we're going to be able to tell what happens to these asymptotes, these horizontal and vertical asymptotes. All right, so let's talk about all the different types of asymptotes then that there could be on a graph like these rational functions. There could be vertical, so we talked about that. That's anything that's x equals a number. The vertical asymptotes come from where the denominator is equal to 0. So anywhere where the denominator is equal to 0, those excluded values, if you think about back when we talked about domain, that's where your vertical asymptotes will come from. Now you have to be careful though, because where the denominator is equal to 0, you need to check to see if the factors are removable. In other words, leaving a point discontinuity instead of a vertical asymptote. So we got to double check those point discontinuities too. So just because it's excluded doesn't mean it's going to leave a vertical asymptote, only if it can't be removed. All right, the next kind again is horizontal. That's what our parent graph had. The horizontal asymptotes come from y equals a number. Horizontal ones then are the places where we look at the end behavior of the graph. What is y approaching? So the end behavior, y approaches what as x approaches positive or negative infinity. So what's happening at the ends of the graph? So we have some shortcut ways of looking at that too. And then the third type, which is what we're going to talk about in part 2 of 3.7, are slant asymptotes. Those are ones that are y equals mx plus b, so actual linear equations. And those come from actually looking at what the ratio is. So we actually divide to figure out what that is. We divide the f of x divided by the g of x. See what it's approaching as x gets really, really big and really, really small. So looking at those slants. So today, this first part, we'll do vertical, horizontal, and then part 2 will follow up with slant. All right, so we're going to focus our first part here on just the 1 over x family. What transformations do they have and what effect does that have on the asymptotes? So let's take a look at this first one. That -3 with the x, that means your graph is going to go right 3. So if we move our graph, it moves where those asymptotes are as well. So if you think about moving to the right, that's going to affect your x values. That means that's going to affect our vertical asymptote. All right, so what would the vertical asymptote be? Always comes from when is the denominator 0. So that means at x equals 3, we're going to have an excluded value. I can't remove the factor x minus 3. I can't divide it out, which means I'm going to have a vertical asymptote at 3. which makes sense, right? If you just think about the transformation, just doing the graph, you'd pick up that graph and move it over 3. That means the asymptote goes with it. Okay, horizontal. Horizontal comes from the end behavior of the graph. This one doesn't have any transformation up or down, so it's going to have the same horizontal asymptote the parent graph does, which is y equals 0. Because again, think about what happens to the whole equation. As x gets big in the bottom, that means the fraction's going to get smaller and smaller. So y is going to approach 0 as x approaches plus or minus infinity. So my horizontal asymptote would be y equals 0. Go ahead and type it in your graphing calculator to see that. It's just our regular parent graph. All right, then we're going to do a rough sketch, but I know it's over 1, up 1 if it's not stretched. That didn't quite attach. And then left 1, down 1. So rough sketch of what that graph would look like. So asymptotes move with those transformations. All right, let's try another one. Take a look and see what happened to this graph. Go ahead and think it through, jot it down. You can pause if you need to. So this graph went up 1. It was reflected over the x-axis, and it's a vertical stretch. So the only one of those that affects asymptotes is that one. All right, let's talk about the types it would have then. So vertical first. So it has vertical asymptotes whenever you have undefined places. So whatever makes that denominator 0 is going to be a vertical asymptote if you can't remove it. I can't remove that x, so there's definitely going to be a vertical at x equals 0. So it didn't move left or right at all, that's why it stayed put. Okay, horizontal. Horizontal comes from the end behavior. So this horizontal, we need to look at y approaches what as x approaches plus or minus infinity. I'm going to go ahead and have you graph this. So if you need to pause, go ahead and do that. But we're going to go ahead and graph this equation and see what that looks like, just so you can kind of guesstimate what's happening. So plus 1. All right, when you look at the graph, I want to see what it's approaching. Now, remember when we were talking about end behavior, we looked at ways you could check. You could go to your table and arrow forward. You can trace on your graph. But when you do that, it sure looks to me like this graph is approaching 1 at both ends. So I'm going to fill in that number. It looks like y is approaching 1. Think about what that transformation did. A plus 1 is going to move that graph up 1. That means my horizontal asymptote moves with it. It has to be at y equals 1. All right, so if you know what that parent graph is doing, this fraction would go to 0. Add 1 to it, it's going to go to 1. I'm going to make a super rough sketch here. We know it's reflected, so instead of being in 1 and 3, it's going to be 2 and 4. I know you could get points if you needed to. I'm not going to be super concerned about that right now. It would be vertically stretched, but the graph would look something like that. Alrighty, let's try a couple more of these parent graphs with 1 over x. All right, so it's our 1 over x parent graph. Tell me what it did. So go ahead, pause, jot it down. So this one went right 1, up 2, and a vertical stretch. All right, so what does that mean for our asymptotes? The only two that affect asymptotes are the first ones, the up, down, and the left, right. So let's talk vertical first. Come from where the denominator is equal to 0, which would happen at x equals 1. That's our undefined or excluded value. So x equals 1 is where our vertical asymptote is going to be. I can't remove that. I can't get rid of that factor. I am stuck with this. It's not a point discontinuity. All right, horizontal. The horizontals come from the end behavior. So y approaches what as x approaches plus or minus infinity. Now you can graph this one if you want. You're welcome to do that, but think about what that up 2 does. That means what was at 0 is going to move up 2. So y is going to approach 2 at the ends of the graph. So this first fraction is going to go to 0. 1 over x always goes to 0 because the bottom is going to get bigger. So 3 over x minus 1, it's still going to go to 0. Plus 2 then means you're going to have a horizontal asymptote at 2. All right, now, general shape of the graph, it's not reflecting, so it's going to be in 1 and mostly 3, a little bit of 2 as well. So just getting a rough sketch so we have a picture, and I know it's vertically stretched. So those asymptotes move with the graph. All right, let's try our last one of these, and we'll move into non-1 over x, get a little bit more involved. So what happened to this one? Go ahead and pause. What happened to h of x? So it looks like we went right 3, we went down 2, and it's a vertical stretch. And again, the only two that affect asymptotes are the first two. All right, so let's talk about vertical. Set the denominator equal to 0. Find your excluded value would be when x equals 3. So our vertical asymptote, can't get rid of it, can't remove it, can't divide it out. So we have a vertical asymptote at x equals 3. All right, horizontal. The horizontal asymptotes come from the end behavior. Y approaches what? As x approaches plus or minus infinity. So what is y approaching? Well, what did the transformation do? It moved the graph down 2. So our original fraction, the 1 over x family, that goes to 0. The x gets big, that bottom gets big, fraction gets small. Then we subtract 2 from it. That means it's going to approach negative 2. So your horizontal asymptote will be down at negative 2. For any of these, go ahead and graph it on your calculator so you can see what that looks like. All right, now it's vertically stretched, it's not reflected, so I'm going to go ahead and put it in quadrants 1 and mostly 3. A little bit into 4 as well. So it's a really quick and easy way to be able to graph those. So your 1 over x family always have asymptotes at 0 and 0, so x equals 0, y equals 0. Unless you move the graph, then they move with. All right, let's take a look at a couple to finish up this part 1 that are not just regular 1 over x. So take a look at this one. It's a little bit different, right? So see if you can figure out what's different about this equation. Well, it looks like we have an x in the top and we didn't have that before. I want you to go ahead and graph it on your calculator. So x divided by x plus 1. See if this graph looks similar to the ones we were doing before. Sure looks like it, very similar kind of graph. Now, if you look at the picture, it looks like we have a vertical asymptote and a horizontal. See if you can guess from the graph where it is. Looks like the vertical happens at negative 1. So let's talk about that part first. Still a rational function, still a ratio, so I still have to worry about what makes the bottom equal to 0. And that would be at negative 1. And again, if you look at the graph, that makes sense for what you're showing there. I can't remove x plus 1, that factor. It can't be divided out, so you have a vertical asymptote. All right, let's talk horizontal for a second. Horizontal asymptote, what is y approaching as x approaches plus or minus infinity? Well, as I said before, when we look on the graph, it kind of looks like it's going towards 1. You could trace, you could do table, but it sure looks like it's going towards a 1, which means my horizontal asymptote then would be y equals 1. Now, there's a way to sort of figure it out from the equation too. When you looked at the 1 over x family, it always went to 0 because that bigger power was on the bottom. You were dividing by x. X gets big, fraction gets small. This one, take a look at the top. The degree in the numerator is a 1. The degree in the denominator is a 1. That means they're equal. They're balanced. They're growing at the same rate. When the degrees are equal, that means your horizontal asymptote is going to go towards the ratio of those highest degree terms. The other terms don't matter, it's just the highest degree. So when they are balanced like that, when they're equal, that means the horizontal asymptote is going to be equal to the ratio of those highest degree terms, which in this case is the x, which means it's going to go to 1. So if you know they're balanced, when the degrees are equal, that's a great shortcut to look for what should it be approaching, whatever the ratio of those highest degree terms might be. Often that's 1, but it doesn't have to be, right? You could have coefficients in front as well. All right, let's try one more of those. All right, so take a look. We want to see what's going on for this one. I'm going to go ahead and type it in. So go ahead and pause if you need to and type yours in. So we have x squared minus 2x minus 3, and then divided by, make sure you use parentheses on the bottom so you get the whole denominator here, plus x. Okay, when you look at this graph, I want you to think about vertical asymptotes for a second. I'm only seeing one vertical asymptote. Looks like it's happening at 0, and it looks like we definitely have a horizontal asymptote again. If you kind of trace or use your table, looks like it's approaching 1. Let's talk about what's happening though. I only see one vertical. All right, so vertical asymptotes come from, again, where your denominator is equal to 0. So if I solve this as a denominator that has degree 2, I have to factor it. So make sure you factor it. That would give me 2 excluded values. I can't use either 0 or negative 1 in the domain of this function. They're both excluded. But let's look back at your graph. How many vertical asymptotes are there though? There's only the one at 0. This one is a vertical asymptote. This one isn't. I know it's still excluded though, right? Look at your table, says error. So what's going on? Why is that one not a vertical asymptote? Okay, remember the whole idea about checking to see if your factors are removable. So if you factor the top, what factor can you remove from that fraction? Well, I can take out the common factor of x plus 1. That's this guy right here. That's not going to be an infinite discontinuity then. It's not going to leave a vertical asymptote. But what kind of discontinuity is it? It would be a point. So it's a discontinuity point. So it's still discontinuous there, right? We still can put that number in, but it doesn't leave a vertical asymptote behind. It leaves a point discontinuity. So remember, if it's removable, that's what's going to happen. That's the most commonly missed thing on the test. People forget about those little details. Okay, horizontal. What is y approaching? It looked like 1 as x approaches plus or minus infinity. So from the graph, it sure looks like my horizontal asymptote is at y equals 1. An even easier way to be able to tell that, though, is look at degree. The degree on the top is 2. The degree on the bottom is also 2. So that means when the degrees are balanced, it goes to the ratio of those highest degree terms, which would be 1. So it's a really quick and easy way to be able to tell that. Okay, so these first two types of asymptotes, vertical and horizontal. Vertical always come from the excluded places. Look at your domain, the denominator, but remember to check to see if they're removable. And then horizontal is always end behavior. So we'll look at when you have horizontal versus slant, which we'll talk about in day 2. But if the powers are equal, it goes to that ratio. If it's bigger on the bottom, it always goes to 0. So if you can kind of remember that, it makes life a lot easier for looking for those. Or just graph it, look at the end behavior.